So I don't have any slides for this. I've just got code. I figured that'll be sufficient enough, since we all pretty much write code daily. So this talk's going to be on spatial data that's inside of SQL Server. We'll go through like an introduction on when it came out, as well as some of the benefits of using it. I've got a whole bunch of links here that for further research and things that have helped me along the way. Then we'll look at creating some actual spatial data, learn about some of the reference systems, and then I went and got the layout for the Kaizen office, so we'll be able to see that inside of SQL Server. Then we'll go over some of the methods that are available to us, some of the file formats that we run into out in the wild, and how to get those into our systems. Then we'll talk about spatial indexing and how to speed up some of the queries that are required for analysis. And lastly, we'll look at envelopes and aggregates and see how all of that can handle larger data sets. So to start out, SQL Server has two spatial data types. Geometry is considered flat, and geography is round. Both of them are .NET libraries, CLR, and they come installed by default with the engine, so there's no need to set anything up. Both data types support points, lines, circular strings, and compound curves are fairly new, as well as polygons. In addition to just single objects, you can have collections, so multiple points in one group, multiple strings together, and so on. So some background is the Open Geospatial Consortium, and they're a nonprofit group who kind of maintains how all systems should function. It's kind of like an ANSI standard, but they have, like, when working with spatial data, you have to follow certain rules, and they try to keep that as organized as possible. And I've listed here some of their documentation in their website, so feel free to look into that more. A couple books. Alistair Atchison has been a lot of his books and blogs have been very helpful. It covers pretty much everything front to back. There's also two very invaluable Redgate Simple Talks from Roy Ernest that is very wonderful. Actually, I will pull one of those up later when we get into indexing. There's also some more details at these two links as well, talking about additional information and more deep dive into it. So spatial data was introduced in 2008 release, and then was upgraded in 2012, where a whole bunch of new, like the circular as well as curved objects were added, as well as some other methods and functionalities. But with 2008 was when it was first introduced to the engine. I've also got a link here to some spatial tools that are very helpful if you need to do work with data outside of SQL Server in ways of maybe transformations or trying to get data into the proper format. So like we talked about, here's some of the reference docs for the two different types of spatial data. And then kind of an introduction to how CLR works. It's really just developing a dynamic link library and then assigning it. So in order to show where these are, we can go into our Object Explorer. And under programmability, types, and spatial data types, we have both the geometry and geography, as well as the regular date, time, and character strings. That's where things are located. So with that, let's define a single point. So this is using the geometry data type, and we're just going to create a point at position x, y, 3, and 4. And so we declare that geometry. We can set it by using a parse command, which is the functions that are built into the geometry data type. So when we run this, we receive back a binary result. And so the way the data is stored is not necessarily that string that was parsed, but is actually binary data that's condensed into a format that SQL Server can understand. You also notice in the results we have a new spatial results tab. If we click on that, it'll give us a nice grid of where that point is. But since it's just a point, there's not really any type of visualization that we can see here. It's actually, in the dead center of this.
I see it.
Oh, yes, there it is. Yeah. And so not only can you declare variables, you can just write it in line and perform the exact same operation. So that binary format is defined by the OGC as well-known binary format. So in order to see that information, we need to use some of the built-in functions that are able to expand upon that point and show maybe a little more of what's actually there. So we can use this ST buffer, which will on the fly generate new points and new geography in a way that extends out from its current position. So we'll go ahead and select this and run it. And we get the well-known binary again. And now we see that point. So besides the point, we can also do one-dimensional lines. So here we can define a line string as being empty. We can also say we're going to start from 1, 1 and go to 3, 3. But then there's also ways of if you enter something incorrectly, it'll come back and say that it's not valid. So I've got a query here to check all of those to see if they are valid, and then perform that same ST buffer to expand it out just a little bit to see the actual shape. So we'll go ahead and run this. And so here we see the first 4 are valid, the 5th one is not, and all of the well-known binary. If we switch over to our spatial results, we can see here's the empty one, here's the one from 1 to 3, and then here's the others that, as you see, they're that ST buffer will take into account overlap and consider it as, a single geometry. Now, when you have data that might come in as incorrect or maybe missing parts and pieces of it, something was truncated, it will throw you errors. So this will give us a format exception, and as you see, it's actually quite good in letting us know what the actual error message is, instead of just an error has occurred. It actually knows that, hey, this is a line string, and it tells us that it's improper. So in addition to just using regular parsing commands, we can also use what's called this stgeom from text. So that will specifically say that we want to create a geometry from the text that we're given.
In terms of functionality or usage, what are the benefits, or I guess what are the similarities and differences between parse and stgeom from text?
So the stgeom, it has code. The CLR code is specific to only working with that type of geometry that gets sent. So I didn't show it here, but there's also like st point from text, st line from text. So then it kind of when you're parsing that data, it has a lot of overhead, and it needs to figure out exactly what type of object is being sent to it. Whereas this, you can specify that this is the type of text that's coming in, and so that overhead gets removed.
I see. So it's more performant, and also kind of allows you to assert what you expect to find. So if you find a point in the list of lines, you know that it's not supposed to be there.
Correct.
Okay.
Yes.
Okay, thanks.
And so you notice with these functions, there's this 0 in it. So we're not just parsing a piece of text, we're also passing in this 0. And the 0 specifies the spatial reference ID, or SRID, for the geometry instance. And I've got a link here that goes into a little more detail about it. But what SRIDs are is the definition of the math required to calculate the projection of our data onto a map. So when working with flat Earth, the geometry, we need to know what that the ellipsoid is of the Earth, and have that curve be applied to the data that we're working with. So when we're trying to calculate distances and things, it doesn't alter or skew the results. We're fitting it to the actual globe.
Is there a predefined list of spatial reference IDs that you pick from?
Yes, absolutely. All of the data comes back in meters, but we can also specify different things. So this all comes from geodesy, which is the study of Earth and its geometric shape.
Okay.
The other like formats that you were asking about is controlled by the European Petroleum Survey Group, which is now considered the International Associate of Oil and Gas Producers. And so these are guys that are going out and looking for drilling oil and gas. So they're very well knowledgeable about geospatial information, and so they created this SRID system where many different if we're operating in Australia, they may have different formulas or characterizations about how they want to map, their continent versus, in Europe somewhere.
Got it. Thank you.
Yep. And so here's another link for the spatial reference system. So SQL Server comes by default with a list of pre-built, what's commonly known SRIDs. So if we take a look at them, we can see that the result set is 391, and the unit of measure is in meters. But as we see, here's the name of the type of system that we're wanting to use, and then the different degrees and things in order to project that into that type of coordinate system.
Mm-hmm.
The one that is most frequently used is 42. Wow, I'm sorry, I'm blanking. Let me switch back. 4326. I apologize. 4326 is this World Geo system from 1984. And so most of the time, whenever you're running into spatial data from other sources, a lot of the vendor systems that I've worked with is usually in this type of format. This is the kind of the normal way we look at latitude and longitude, being maybe 2 or 3 decimals, as opposed to some of these others could be in millions of digits, or in the millions of units. But this one is like the standard for all mapping.
Mm-hmm.
Here we go. Yeah. and if you want to know more about about that system, I've got some links here.
Mm-hmm.
So I thought it would be a good time to check out our facilities. So here's the Louisville office and the Cincinnati office. So if we go out to here, we've got that latitude and longitude, and there we are. And then we also have Cincinnati, and where their office is, our other office is located there.
Mm-hmm.
And so what I went in and did was, in order to capture these points, I just clicked here, and was able to obtain the points down below.
Mm-hmm.
And so as you see, it's a rectangular. So if we switch back over, here is the Louisville Kaizen office being displayed, and notice the ST poly from text,
Mm-hmm.
and we're giving it the 4326, and we're specifying the longitude and then latitude for the polygon. So when we run that, we get the well-known binary and the shape of our office.
Mm-hmm.
So from there, we can also see some of the methods that are available to us. We can define the area, the length, how many points. If there's multiple geometries within our collection, we can see that. We can also see where it starts, where it ends, as well as a whole listing of other things there. So if we take a look at that, run that, we'll see the area is about 800 meters. There's 5 points. And the reason, instead of just 4 points, that fifth point is actually the first point just added again to like close that loop. And we also can see the binary as well as the text directly from that geometry object. So there's like a bunch of metadata behind these data types that can be obtained by just a period and then the method call. A lot of the different shape files that we run into, well, shapefiles is the one that we run into most. It was developed by Esri, who is kind of the de facto of GIS technologies. Tiger is also another one that is heavily used by government officials. GeoJSON is fairly new. It's kind of a more lightweight and easier to read, and it's not a binary or proprietary format, as well as KML and GML. Those are kind of the back in 2008 when all this was first introduced. XML was real big news and was used by a lot. So those two formats are in XML. So for the demo part of this, I wanted to get a data set that we all might be able to relate to. And so the wind turbine database is handled by the federal government, and you can get the like technical specifications from this website. In addition, besides just seeing a bunch of dots on a map, why don't we see the actual states that they're in? So I was able to find the Tiger map of all of the states. However, since earlier this week, the Census Bureau has updated their website, so that link is bad, and so I was able to find it located here. So if we switch back to Google, nope, here. So this is the USGS website, and where they have this wind turbine database. And there's all sorts of information about it, and they keep updating it quite frequently. The geography mapping files are located here. I specifically had the 2017, but it looks like there's on this new site, it looks like there's actually this year's data. And they have different shape files and KML files that you can use, but I was using the Tiger shape file. So we'll switch back to here and take a look at our windmill load. So we have a file. Well, let's first define how our data is going to be structured by creating a table. And then tables must have clustered primary key in order to allow for geometry or geography to be used within the table. So this data comes as a GeoJSON. So we want to read it from the disk, assign it to a variable, and then from there we can use the new OpenJSON feature, which was introduced I think 2017, 2016, and be able to use this with command to go through and parse out the GeoJSON. So it starts with a collection of features, and then we can dive into the properties and then obtain all of the properties associated with that file, and then insert that into our mill table. And then I got rid of this one in particular because it was kind of an outlier. It's over in I think Guam.
Okay.
Just to keep it consolidated. So I'll run this again just to refresh that table. And as you see, here's a listing of all of the states and how many wind turbines are in each state. So, there's quite a few in some of the flatter states, Texas having the most. Okay, so now we've got a mill table loaded, but let's take a look at it and just see. So this is a much larger data set, and having multiple geometries associated with it. So the spatial results can only handle up to 5,000, and so that's all we're going to see is the first 5,000 that came through from our results. So if we zoom in here a little bit, we can see that there's clusterings of wind turbines at specific locations that the group that builds them and the manufacturers have determined that these are the best spots after doing years of wind studies. So the next one is the states data. It was a little different from a shape file to a GeoJSON. I used some specialized tools in order to convert that. I won't go into detail about them, but I should have put a link on here on how to do that. There's a whole open source community around some of these tools that allow you to do conversions between different file formats, as well as putting them into certain databases, like if it needs to go into Postgres, there's certain drivers that are available to do that conversion. But there's also a mapping server that can read this data and serve it out to any type of like REST or web service, and be able to ingest that data that way. But for this, we've just got GeoJSON, and this is a little bit different because we're needing to parse it and actually get the geometry out of it, whereas before we had a listing of just XY locations. This is actually a collections of polygons within the JSON file. So this is where we parse out and get the coordinates as well as some of the properties. And I removed a few of the states because it showed they were kind of outliers, and wanted to keep it just to the handful of states that we're in. And then, yes, I'm using a cursor to go over each set of polygons that are inside. Even if there's multiple polygons, I wanted to be able to extract out just the polygon represented by the state. And we'll see that a little bit more in a few moments. But if we go ahead and run this, it does take a minute, to go through 803. But as you saw, 12 seconds, that's not bad. But then if we switch to the spatial results, here's all of our states. And so, we can see here's Tennessee as a polygon, Kentucky, Indiana. So, we now have all of our states represented in a table. So now if we go back, And here are just two queries that I had for visualizing those. So let's see what all of that information is for the state of Kentucky. So there's two results here because of the little area that's towards the west of Kentucky. So you have this smaller one which only has 42 points, and the larger portion of the state has 3,000 points. And so Kentucky Bend. So if we take a look at the states and just view the geometry, we can see, yep, here's the larger portion of the state, but then it changes color for us automatically, and then that's the Kentucky Bend that's out there. So what are some of the possible ways of combining these two data sets? In order to do that, I've selected Indiana and from both data sets, and we're going to combine both the state shape and all of the windmills that are associated to the state of Indiana. And we have to use a union all and not a union when working with geospatial data. Mm-hmm. So if we run that and view it, we can see here's the state of Indiana, but then here's a large cluster of windmills that are in northern part of Indiana. So from there we can say, well, what if some of them are misidentified or not calculated properly? They're classified incorrect, but we want to determine that a point is actually within one of those polygons. So we can use what's called the st-intersects, and that will say, is this mill, its geography, intersecting with that state geography? And if it's 1, then we want to see that result. However, this query can take a large amount of time. It's still continuing. In order to find all of that, we have to look through every single windmill and see, is it located anywhere at all in that polygon. So if we have windmills that are in California, it's still going to parse those, even though we know that it's miles apart. Mm-hmm. So we need a way to speed this up, because if we don't necessarily want to crunch numbers for things that are irrelevant to where it's at in the states. Mm-hmm. So I'll go ahead and just stop that. So we've got 58,000 windmills and then 803 polygons of the states, and so that's 46 million combinations that it's trying to determine. So in order to help speed that up, we can use what's known as spatial indexes, and so they actually will behind the scenes create grids, very similar to how B trees work, and saying that this point is actually located in this grid, and when it's doing these types of computations, it can use that B tree in order to go and find it much faster than it would than scanning the whole data set. And so a really good example of that, I believe it's this one. Yeah, here we go. So there's multiple levels, and so our first level is kind of like at a state level, and then we can look at maybe a county level, and then maybe a smaller portion all the way down to your address, is how that kind of grids out the index for us. That decomposition is what they call it, in order to quickly identify a location of an object. So we can create on our mill as well as our state table bounding boxes, and I've found those by obtaining. We'll get into that shortly, but there's a way to calculate the boundaries of our positions within the entire data set, so we can stay within. It doesn't have to go and look at in Europe or something. We can keep it maintained to just where we want to search. So I'll go ahead and run those. I'm sorry, we are over time. So we'll run this, and this is on the entire data set, and it should only take about 10 seconds now that we have that new, our 2 new indexes on there. And there it goes for 58,000 records. So just real quick, in order to determine the bounding box, I use this union aggregate, and so that will take all of those points and see we only have one result record. It joins them all up into a single object that can then be displayed a little easier. We can also do that and include the envelope, which will tell us the boundary points of where everything is located. So we should have 2 results back, one for all the points and then one for the min and max of each point. We can also do envelope aggregates in order to determine what those values actually are. So we have 5 points, which once again, it's the start and then all the way through and then the start point again. But then to obtain the actual points, we need to tell it to cross apply 5 results, and then that'll tell me each point and what their XY coordinate is. And then perform min and max on them to determine what the actual boundary box is. And so that's how I was able to obtain the numbers from previous for the index.
If you create an index for a certain bounding box, and then later you insert a record into the table on which the index is built that is outside of that index, is it kind of equivalent to filtered indices where the data that's outside of it will simply not be indexed and will be searched without the index?
Correct. Yes. Okay. Yes. And if something like that were to happen, it's best to try to find that boundary again and re-index. Yeah. Yep.
Okay.
So that's pretty much all I had. We were able to go through and see, how when it came about in 2008. Went through some of the information on how the different organizations, how they keep track of things, and then was able to see an example of all the windmills in the United States. So yeah,
that's really cool.
Very cool.
Yeah.
Yes. know that you have already done quite a bit of work with geographic information systems. I guess a lot of that with LG&E. Could you share some examples of interesting things that you have done that relied on SQL Server for geographic data analysis?
Yes. So one of them is their lightning analysis tool. There's a company called Vicela, and they use radio waves from thunder as determining where a lightning strike is, and they have an algorithm that can tell them where the probability of that lightning strike occurred based upon the thunder. And there's multiple of these around the United States, and they're always running and they're always collecting data. They're also global, but that data then goes to I think it was in Colorado where they're based, and then they kind of sell that data to a lot of different companies, and LG&E is one of them. So we were able to purchase a new server to have them ship that data to us. And so similar to like a bounding box, we defined what that boundary should be and only receive lightning strikes in there. So originally that was that's all done on Red Hat and Postgres. So what they tasked me with was, well, we want to get that and show it with some of our other, bring that into our data warehouse so we can show that with other assets. So I was able to create a SSIS package that every 20 minutes goes out and gets, the newest results, and then go through and index it, as well as apply it to their transmission network system and see, where was a lightning strike, a mile away from a certain transmission tower, or was it a foot, with a direct hit. And being able to do that by creating these indexes, and like the ST distance is another one, and determining how the probability of where that strike occurred, we were able to then bring in their outage app data, where if there was a line tripped or some failure occurred, that gets recorded, and then we can assign based on the time periods and that structure, we can determine that, yep, that outage occurred with that lightning data and their transmission network data to say that, yeah, it's a good probability the reason it's on fire is because of lightning.
Mm-hmm.
So
that's an awesome
yeah.
application of,
Yeah.
of a lot of I guess a lot of transformations and steps to produce very interesting results.
Yeah, it was a lot of fun. They still use it today, so.
Yeah, so if you have an outage, you don't know why, ask Lucas.
Yeah, I can find out. Yeah.
Also, I agree with Charlie.
Thank you, Charlie.
Yes, that vote of confidence